Okay, so good afternoon, everyone. I'm Xiang Li, a PhD student from Tsinghua University. And in this talk, Phoenix domain attack, vulnerable links in the domain name delegation and revocation. I'll introduce a new DS cache injection attack, which could make a revoked domain continuously resolvable on some vulnerable resolvers at a large scale. So in the following, I will focus on how we find it, how we measure it, and propose some mitigation solutions. So to start first, I'll describe the exploitation impact. So even a domain expires or deletes from some TLD zone files, we can still use it to resolve our target domain names for free with our Phoenix domain attack. So in today's internet ecosystem, domain plays an important role. It provides a solid basis for multiple applications and services, such as web browsing, CDN, email, and certificate. And according to verified reports, there are about 350 million domain names that have been registered. However, domain names can be used also in the criminal activities, such as the botnet communication, phishing, and malware distribution. So according to ICANN's monthly domain abuse activity report, in just 1 month for March 23, there are more than 1,620 domains showing security threats. So to fight against the malicious domains, domain name revocation has been proposed and adopted in multiple ways by the registrars and registries. So security operators can use domain revocation to remove malicious domains, such as by deleting or changing the name server. So as expectation, after revocation, domain can no longer be used by the original registrants, such as attackers. For example, for domain revocation has been used for a very long time, such as in Microsoft sees a .org to kill a botnet domain name, and in last year, US sees one of the world's most largest hacker forums. So here is the question: how does domain name revocation work, and if domain name revocation works as desired? And first, I want to explain what is domain name revocation. So when a user wants to register a domain, such as botnet.com, the TLD name server and its operators will add a name server record to the TLD zone file, as in the above line. So after domain revocation, the operator can either deleting the name server record in the zone files or changing the name server to another controlled server, such as we show here the green one, which this way and is called the domain synchrony. So this is how the domain name revocation works. But does domain revocation function as desired? I'm afraid the answer is no, because the goose domain has broken this guarantee. So here I want to explain goose domain first. Goose domain attack is proposed by our lab in 2012, and it aims to make a revoked domain name still resolvable on target resolvers. So here is the high-level workflow of the whole goose domain attack. So before revocation, we assume that the attacker used a domain name named botnet.com. So before the launching the following attacks, the attacker just query the target resolver and make it cache his or her name server record as shown in the bottom, the yellow one. So after revocation, the botnet.com has been removed from the comms TLD zone file. So basically, as expected by the domain name revocation, the other recursive resolvers will never get a valid response for botnet.com because it has been removed from the TLD zone file. However, for the target resolver, the yellow cached record is still alive and have a TTL value. So before the TTL expired, the attacker what the attacker want to achieve is the attacker will query the target resolver again and query his or her own controlled domain. So because the cache is still alive, the target resolver will send the following query to the attacker, the name server, uninstall botnet.com. So this time, the attacker will return a new name server record with a larger TTL value. So because Goose domain leveraged some implementation flaws, the target resolver will consider the newly returned name server record is valid and with a larger trust level. So the target resolver will cache the new name server record and update the TTL to a larger one. So the cache of botnet.com will be refreshed round by round and will be still alive. So here is the Goose domain. And with Goose domain, even after revocation, malicious domain names can still be resolvable on the target resolvers. And attackers can use it to evade some domain takedown or use it freely. So after disclosure, Goose domain affected several DNS software, such as bind power DNS. And as a mitigation solution, the TTL field cannot be prolonged, because if the TTL cannot be refreshed to a larger one, the cache will only be alive for the specified value. So this time, Goose domain is fixed. However, 10 years later, we are still wondering, does the domain name revocation this time works as desired after we fix the Goose domain? Unluckily, the answer is still no, because the Phoenix domain still breaks this guarantee, even with a broader surface. So here is the Phoenix domain. It's also proposed by our lab, and the original paper has been published in NDSS 23. And Phoenix domain also wants to make a revoked domain name still resolvable and target multiple recursive resolvers. And there are two variations of Phoenix domain named T1 and T2. And because the Phoenix domain exploit some vulnerabilities in either the DNS protocol or the implementations. So overall, Phoenix domain affects all the DNS implementations. So before I explain how Phoenix domain work, we wonder why the domain name revocation is still vulnerable. And after we do the analysis, we find that the overall attack surface is still unclear until now. So after reviewing the DNSRC documents and several open source DNS implementations, we summarized the basic DNS cache operations. And there are 4 operations, including the cache searching on the left, and the cache updating and the cache insertion on the right, and the cache deletion at the bottom. So during the cache searching, the resolver will use some closest name server record to do the resolution. So the closest name server means a domain name with the longest domain suffix. Well, for the cache updating, after receiving a valid response, the resolver will check the data level for the cached one and the new returned one. Besides, if there is no cache, the resolver will just cache the received response directly. Well, for the cache deletion, it's a separate process from the others, because if the cache expires, it will delete from the local cache database directly. So after we compare a goose domain and the Phoenix domain, we find the goose domain just exploits the cache updating operation. And the other operations like the cache searching, cache insertion, and cache deletion still pose some security risks, which assisted our Phoenix domain attack. So how does Phoenix domain work? Basically, there are two variations and such two ways. So for Phoenix domain T1, T1 exploits some vulnerable cache insertion implementations. And the key idea is the attacker can inject some new name server records when the old one is about to expire. So here is a key tab. And I'll give a high-level workflow of Phoenix domain T1. So on the left, we give a normal domain resolution process. And the attacker just query the target resolver and make it cache his name server record. So here is the first step, and is a crucial one, because the attacker needs the target resolver cache his or her own name server record. So after domain revocation, we use the domain deleting for the com.tld domain file. So after domain revocation, botnet.com is theoretically botnet.com should never be resolved and should be invalid. However, for this time, the attacker just wanted the target resolver to refresh the cached name server record. And as we mentioned before, because goose domain, the TTL value will never be refreshed to a larger one if there is a cache, if the cache exists. So the key idea is we can return a response when the cache name server is expired and removed from the local cache. So what the attacker is doing is choose the dedicated tab and return the new name server record. So how does the attacker choose this tab? Here is the detailed attack steps. So before the attacker do the cache insertion operation, we assume the target resolver has cached the name server record we need. We can see on in the cache, the name server record of botnet.com has a TTL value about 1 day and has a TTL value to expire. So the first step is the attacker needs to choose the time to query the target resolver. So what's the time? It's a time that have a delta TTD value for the cache to expire. So after receiving the query from the attacker, the target resolver will perform the recursive resolution for botnet.com. Because the cached name server is still valid, the target resolver will send the botnet.com query to the attacker's name server. So after receiving these queries, the attacker just holds these queries and delete to return the response for a delta TTD time. So after this time, on the right, for the target resolver, the name server, the cache of name server expires and removed from the cache. So at this time, the attacker returns the new name server record. Because there is no cached name server record, the newly returned one will just be cached directly and bypass the mitigation solution to restrict the goose domain attack. So this is how the Phoenix domain T1 work, and the following is the T2. Well, for this one is maybe a more tricky one. So T2 attack exploit vulnerable cache searching operations. The key idea is the attacker tries to inject some new name server record of some subdomains to the cache. So on the left, the same steps we need to inject the normal name server record before the revocation. So after domain name revocation, the attacker just query the target resolver and query some subdomains. Maybe for this stage, the attacker queried the s.botnet.com. And well, for the target resolver, because the validation of the cached name server record, it will send queries to the attacker name server, and the attacker will return the name server of the subdomain to the target resolver. So because the name server of the subdomain has never been cached, the target resolver will just query the new name server records directly. And because according to the DNS specification, the max label number is more than 100. So the attack round can be performed iteratively more than 100 times. So the overall cache lifetime for this T2 attack is 100 times the single TTL value. So if we assume a single TTL value is 7 days, the overall cache lifetime could be more than 2 years. And here is the T2 attack. And because the subdomain resolution is a de facto practice by all the DNS software, T2 affects all the DNS implementations. So for the two attacks, we tested each DNS software and find the Phoenix domain T1 affected 4 software, such as Bar9, Not, Unbound, and Technetium. Well, for Phoenix domain T2, because as I mentioned, it exploits the de facto DS recursive resolution process. It affects all the implementations. And for these 2 attacks, we got 9 CVE numbers. Besides, we also tested Phoenix domain attacks on 41 public DNS services. And all resolvers are vulnerable to either T1 or T2, such as Google and Cloudflare public resolvers. And they all confirmed our attack and fixed their services. Furthermore, we try to evaluate the impact of our attack. So we collected a resolver list and containing 1.2 million resolvers, and choose the recursive resolvers from this list. So to evaluate the T2 attack, because T1 is related to 4 specific DNS software, we first conduct a short-term experiment. Because let's recall T2 T2 depends on the maximum labels of the domain name. So we want to check how many labels are supported. So after the short-term experiment, we identified that 89% of resolvers are vulnerable. And after we perform the cache injection 100 rounds, there are still 42% are exploitable. Then we conduct a long-term experiment to see how long Phoenix domain name can survive after revocation. So results show that after 1 week, there are still 40% resolvers are vulnerable. That means if we send a query to these resolvers, we can still get a valid response. Then we continue to observe these resolvers for 1 month, and the results show there are still 24% are exploitable, and which also demonstrate our attack's feasibility. We also draw the picture for the geolocation of vulnerable resolvers, and as the picture shows, the impact is widespread, and all the users using these resolvers are affected. So after we proposed these attacks, we also proposed and discussed 6 mitigation approaches with all the affected vendors. For example, mitigation number 1 is we propose that the target resolver should to validate the name server, because if the name server record expires, there is a chance that the resolver can inject a new name server record. And for mitigation number 2, the recursive resolver can trust the name server from the parent zone more than the child one. And then another maybe short-term mitigation solution is the target resolver can use a small TTL value, because as I mentioned before, if the single TTL value is 7 days, the overall cache lifetime could be 2 years. If we reduce the TTL value, it can also reduce the impact of our Phoenix domain attack. Besides, for the mitigation number 1, it has been referenced by RFC draft, and it is in the standardization process. So in the end, I want to give maybe some takeaways, because for our Phoenix domain attack, we reviewed all the DNS-related RFC documents and 8 DNS software implementations. We found that for the DNS RFC and specifications, they are not very clear enough to provide a deterministic definition of each operation, because the ambiguous of the implementation, there is still a chance for us to find exploitation maybe ways, and we should check the RFC's essential specifications. And for the second one is about the DNS implementations. And after the analysis, we find there is a huge inconsistency between different DNS software, even for same operations. And we also exploit this inconsistency to propose our Phoenix domain T1 attack. And basically, use one word to mark a Phoenix domain T1 is use and check inconsistency vulnerability. So the last one is about the original DNS mechanism, because DNS is proposed more than 40 years ago. Maybe for some new types of attacks, it is not enough to defend this, and maybe we should propose some new patches or redesign maybe some implementation structures for some DNS software. Yeah, so here is my share today, and if you have any question, feel free to use the microphone. Thank you.